Good afternoon, everyone. Thank you for joining me for today's ILDFA technical webinar. We've got about 13 people on the call right now. We're expecting quite a few more to join, and typically folks jump on a little bit late for these things. So while we wait for everyone to join the meeting, I'm going to give kind of an introduction and cover some housekeeping notes. First thing, I'm sure everyone's noticed, mics are muted, cameras are off for the duration of today's webinar. This helps teams to run smoothly as we go through today's presentation. In addition, this webinar will be recorded, and that allows us to share this presentation with folks after the fact. So everyone who is attending today's webinar will be able to go back and review the recording. And Safespill is currently working on a process for uploading these to our website so that people can go back and reference them later and access them if they did not initially attend. So for today's presentation, we're focusing on a specific topic that's really important for ILDFA design, and that is layouts and sizing for ILDFA in aircraft hangars. In the past, I'm sure a number of you, if you're familiar with Safespill or ILDFA, have probably attended a webinar that was more of a broad overview of what ILDFA is, who Safespill is, and some of the key background points on this technology. We're really working on providing more in-depth and focused presentations moving forward for those of you who already understand the basics, right? So this is kind of a next step webinar where we're gonna dive into a specific topic and go more in depth on specifics around layouts and sizing for ILDFA. My name is Giubbini. I am the lead product engineer at Safespill. I've been with Safespill for about 10 years. I've been involved in all aspects of product development, fire testing, code development, and also worked on the manufacturing floor as well as out on some job sites. My experience has involved code development around ILDFA, both within NFPA, U.S. Department of Defense, and Factory Mutual. ILDFA was first included in the 2022 edition of NFPA 409. Just recently, the 2026 edition of NFPA 409 was released. So if you haven't had a chance to go look at the new edition, I do encourage everyone to go see the changes that were made in that edition. I've been a technical committee member since 2022. So have been involved in the inclusion of ILDFA and some of the changes around ILDFA within that code. In addition, Safespill has worked very closely with the U.S. Department of Defense, mostly on U.S. Navy projects, and initial guidance was provided for ILDFA and hangars under NAVFAC ITG. UFC 4.2.1101 is currently being updated. We're pending release of an updated draft of that code guidance, and we will touch on some aspects of what's going to be new in that code during today's presentation. And then finally, on the FM side, the Safespill floor is a FM approved product. It was evaluated under a new product approval standard, which is standard 6090 for ignitable liquid drainage floor assemblies, or ILDFA. I was involved in the initial testing for our FM approval in 2017, as well as our second approval that was obtained in 2020 with some critical design improvements. And then finally, FM has property loss prevention data sheet 793 for aircraft hangars. We will touch on this document today, but this is the 2022 edition where ILDFA was included. So with that, we're going to jump into today's presentation on layouts and sizing. Just first of all, I want to point everyone to some valuable resources that Safespill provides online. At our website, safespill.com, under the technical specs and resources, there's some really important documents that can help in guiding engineering and design firms on early stage planning for ILDFA. Most notably is our ILDFA design guideline. This is a document that we update 2 to 3 times a year. with lessons learned on ILDFA, provides a lot of background on what the system is and how to best apply it in hangars. The most recent revision of this was released in October of this year, and we recently updated it with Spanish and French translations in addition to the original English edition. We also have a number of white papers on the website. Most notably, we recently released a white paper on containment and drainage options. So this covers potential layouts for oil water separators and containment tanks, both above ground and below ground, that can be a really valuable resource when addressing that side of things. I also did a webinar back in September that discussed specifics around containment tank and oil water separator options. And we're working on getting that uploaded to the website in the future. So you can access that if you weren't able to attend. Today's presentation, I will touch on some aspects just in a general sense around cost, just about reducing cost in some areas. But really this presentation is focused on the technical side of things. We're not going to discuss specific pricing terms or contracting. However, we do have a number of cost comparisons on our website to evaluate the cost of ILDFA versus foam in a hangar. And then finally, Safespill has conducted a substantial amount of fire testing on the ILDFA system. All of those test reports and videos of those fire tests are available on our website. So for today's presentation, again, we're focusing on layouts and sizing for ILDFA. This is expected to be kind of the next step, going beyond the basics of what the system is. But for anyone who's attending who doesn't have kind of, or is new to Safespill and ILDFA, I am going to show our explainer video. It's only about 2 minutes, does a good job of explaining the background on how the system works, and hopefully that gets everybody up to speed so that we can go a little bit deeper on this discussion. From there, we'll go and look at the specific code provisions that discuss layout and sizing for ILDFA in NFPA, FM, and the UFC. We'll discuss Safespill's methodology for using spill radius to determine required footprints for ILDFA. We'll talk about some important parameters related to Safespill's manufacturing capabilities and constructability requirements involving zone sizing and trench arrangements in hangars. And then building off of all of this, we'll go through some example layouts from projects that we've either completed or currently in the install and design phase for. Finally, we'll close with Q&A. So this presentation, I do expect it to take about 45 minutes. If you do have questions during the presentation, please put them in the Q&A within Teams, and I'll go through and answer those at the end to the best of my ability. I do want to keep today's discussion focused on layouts and sizing. So if there are questions that you have that are maybe off topic, I can follow up with you after through email or a call to go through those. So just to kick things off, I'm going to start by showing our explainer video.
In hangars, fuel spills during aircraft maintenance are not uncommon, and they are a dangerous fire risk. But if you remove the fuel, you eliminate that risk. With the Safespill floors, spills are immediately removed and contained. Let's look at how Safespill floors work. Generically known as an ignitable liquid drainage floor assembly, ILDFA, the Safespill floor system consists of hollow aluminum extrusion profiles with a perforated top surface. The floor uses the existing slope of the hangar slab to drain spilled liquids through channels into covered trenches. The trenches slope outwards into a drainage box, ensuring all liquids are removed from the floor. There, sensors activate pumps to extract the spill out of the drainage box, typically into an exterior containment tank. A liquid seal trap ensures that no ignited vapors travel through piping to the tank. Now, let's look at the flushing system. The typical slope of a hangar slab is 1% or 0.5 degrees, resulting in a relatively slow drain rate. To accelerate spill removal, A water-based flushing system is integrated into the Safespill floor. Each zone has dedicated liquid sensors to activate flushing only in the zone where a spill occurs. When activated, the flushing system streams a water spray of 1/4 gallon per minute or 1 liter per minute water spray into each channel only in the floor zone experiencing a spill. Each floor zone needs a water supply of about 50 gallons per minute or 200 liters per minute. Once sensors detect liquid in the zone, they signal the control panel, which in turn signals a solenoid valve corresponding to that zone. The solenoid valve connects to a pressurized flushing header that runs through the trench. The maximum water supply required, applicable if a spill falls on a corner, activating 4 neighboring zones simultaneously, would be 200 gallons per minute or 760 liters per minute. Most hangars can supply this capacity from a standard domestic water line. Water can also be sourced from the building sprinkler system or a dedicated flushing water supply tank.
So that's our explainer video. That's again available on our website if you want to go back and look. Again, just covering kind of some background to get folks up to speed if this is new to you. Safespill has been installing ILDFA in aircraft hangars since 2020. Our first hangar installation was at Naval Air Weapons Station China Lake. This was a retrofit installation inside of some tension fabric hangars. We installed 2 hangars side by side, each about 8,000 square feet of flooring or ILDFA, and these were capable of housing up to 3 F-18s. The second project that we completed was at Naval Air Station Point Mugu. This was a larger application, about 18,000 square feet of flooring. And this hangar houses C-130s like you see on the screen, as well as some P-3 aircraft. Initially, all of our projects were with the U.S. Navy because this hadn't been accepted by NFPA 409 or FM datasheet, and so we were limited to working on projects for the U.S. military. But since the inclusion of ILDFA in NFPA 409 in 2022, we've begun doing a lot more projects on the commercial side of things, as well as working with other departments of defense like the Canadian Forces. An example of these commercial projects is installation that we did for Avianor MRO facility up in Mirabel, Canada. This was a new construction facility with 4 maintenance bays. Each maintenance bay always services the same aircraft. So this was a good candidate for a parking spot configuration where we know exactly what aircraft are going to be in the hangar. We know the exact locations where they're going to be parked. So we're actually able to reduce the footprint of this flooring system, covering about 10,000 square feet in each hangar bay. In comparison to that, again, on the commercial side, we did a wall-to-wall application at Jackson Hole Airport. And this is actually an FBO facility, but they do have 1 hangar bay where they do maintenance operations. And so we installed ILDFA in that hangar bay. This is wall-to-wall, so it provides flexibility for parking configurations. Various aircraft are coming in. And so because of those potential unknowns, it was best to cover the maximum extent of the hangar and provide the most flexibility for this facility. So why do layout and sizing matter? This is a really important early stage step in the design process, just to make sure that design is on track and aligned with what Safespill is capable of providing, as well as what's going to be best for the end user. So it's really about striking a balance between cost effectiveness for the system while still maintaining a code compliant and effective solution. So we showed in the previous slide an example of a parking spot versus a wall-to-wall, balancing these, balancing the type of aircraft, the variety of aircraft, and the potential operations in the hangar is going to help determine what's actually going to drive an effective ILDFA solution. It's also important to nail down layout and sizing really early in the design process because decisions on layout and sizing can have effects on other disciplines outside of just the fire protection space. So depending on the layout and sizing that's used, certain things like slopes and slab thicknesses for the hangar will be affected. The locations of trenches can have a big impact on structural and civil concern sides of things. And then for contractors who are actually installing the system, having a full scope of where utilities are going to be tied into the flooring, so where plumbing and electrical are going to be connected, is really important for success on the project. This is a really good example of that parking spot versus wall-to-wall layout configuration. This is actually an outstanding proposal that we have for a hangar space with 2 bays. On the left side, dedicated parking spot configuration. This side of the hangar only houses a single type of aircraft. The parking spot locations are predetermined and always known. And so this is a good candidate for reducing the footprint of the ILDFA in this area, so that we're not covering the maximum extent of the hangar, but we're addressing areas where fuel tanks are located, as well as addressing lateral standoff distances or a spill radius around those fuel-containing parts of the aircraft. In comparison, on the right side of this hangar bay, you can see that there's a wide variety of aircraft located in here, variable parking configurations. And so when we have a hangar that operates in this way, it makes a lot more sense to go with a wall-to-wall application, where we're maximizing the amount of usable floor space in the hangar, and not limiting this hangar operator to a specific parking configuration, but allowing them flexibility for a variety of aircraft and whatever operations are needed in that hangar. So diving into code, NFPA 409, again, referencing the location in the 2026 edition. The text has not changed, but NFPA 409 says the floor dimensions shall be large enough to cover all the fuel-containing parts of the aircraft, right? So we're addressing fuel tanks and engines, and address lateral discharge potential. So accounting for that spill radius around those fuel-containing parts of the aircraft. But it does say to do this per the manufacturer's written instructions. So there's a little bit of vagueness here. And really the reason for that is NFPA being a widely used code. We don't want to give too much specifics on top in terms of the manufacturer of the ILDFA system. At this time, Safespill is the only manufacturer, but we didn't want to specifically set out guidance based off of Safespill's design, as other manufacturers may have different spill radiuses that their systems can accommodate. And also, not pigeonholing it to a single aircraft type, because various aircraft might have different spill radiuses. So what does that manufacturer's written instructions look like? For Safespill, we use what we call a spill radius methodology. So during our approvals testing, as well as the testing that was submitted to NFPA 409 for substantiation in that code, we did a series of spill tests where we're spilling water from various elevations at different flow rates, and then mapping out where those spills go on the top surface of the ILDFA. So using this data, we can look back at what NFPA 409 says for the required spill rates that the system needs to handle. NFPA distinguishes between small aircraft and large aircraft. So for small aircraft, that's anything less than 78 feet in length with a fuselage width of less than 13 feet. We want to use a maximum spill rate of 200 gallons per minute. So using our spill maps, we can go to 200 gallons per minute, and we get a spill radius of 16 feet or 4.9 meters. For large aircraft, so that's anything greater than 78 feet in length, greater than 13-foot fuselage width, we use a maximum spill rate of 400 gallons per minute. And this gives us an 18-foot or 5.5 meter radius around those fuel-containing parts of the aircraft. So just to show an example of this, this would be a large aircraft. We've identified here in these hatched areas fuel tanks on the aircraft. Also identified engines on the aircraft, and then from there we've created these spill radiuses of about 18 feet around the perimeter of those fuel-containing parts of the aircraft, and this orange line represents the footprint that would be required for the ILDFA. FM datasheet 793 uses very similar methodology to NFPA 409, using the same small aircraft versus large aircraft distinction, using 200 gallons per minute for small aircraft, 400 gallons per minute for large aircraft. And it says essentially the same thing. Design the floor dimensions to be large enough to cover all of the fuel-containing parts of the aircraft and address lateral discharge from those fuel tanks. FM provides slightly more guidance in terms of trench arrangements, which we'll discuss a little bit further later in the presentation. But essentially what it says, and it provides this graphic, arrange trenches so that if you have a fuel spill, it does not flow under an adjacent aircraft on its way to the trench. So if we were to have, this is our good example, right, on the top. If we were to have a fuel spill up here, it's going to flow down into this trench, and it's not going to flow under an adjacent aircraft on its way there. The non-example, or the example of what not to do, is shown here, where we have a central trench running parallel to the fuselage of the aircraft. And if we were to have a spill at one of these outer aircraft, it would have to flow under an adjacent aircraft to make it to that trench. So a little bit more guidance given by FM in terms of trench arrangement, but from a layout and sizing perspective, really the same whether we're looking at NFPA 409 or FM 793. UFC, again, this is currently in the draft version awaiting release. There's a lot of text here. I've summarized it, and it is similar to the guidance provided by 409, but there's some specific caveats here. So the summary of this is UFC really takes the approach of it's best to provide full coverage of the hangar bay, right? So this provides maximum flexibility for aircraft. If the mission of the hangar changes over time, different aircraft are going in there, we know that we have full coverage in that hangar bay. For Navy projects, specifically stated to always provide a wall-to-wall application. And there's guidance in a table I'll show on the next slide for maximum extents that are required for that. For Air Force and Army, parking spot applications are allowed, but they do require FPE approval if we're going to reduce down to a parking spot. And when we do reduce to a parking spot, it is really important that we define and mark parking locations for those aircraft, just to ensure that that parking spot is going to be, or the footprint of the ILDFA is going to be sufficient for coverage of the aircraft. The other big difference with UFC is that we're not distinguishing between small and large aircraft. We're always considering an 18-foot spill radius from those outer points on the aircraft. So here is the guidance from table 2.1, as well as a couple of figures that are pulled from that UFC draft. Here you can see the maximum extents of the ILDFA footprint leaves some space along the wall. It is critical that the floor is sloped back into the ILDFA in those areas. And then there's also a figure that shows parking spot layouts. It's important to note here that the aircraft clearance bubble isn't what determines the ILDFA footprint for a parking spot, but rather still identifying the locations where the fuel tanks are and providing that 18-foot lateral standoff distance. So sort of to summarize this, here we've got a rotary aircraft fighter jet. If we were following NFPA or FM, these would be considered small aircraft. We would use a 16-foot spill radius. However, if you're using UFC, this would be an 18-foot standoff distance. Going into some specifics about Safespill as a manufacturer and how we approach design of the system, as was explained in the explainer video, we're covering large areas of floor in an aircraft hangar. However, we do subdivide the floor into zones. Our standard zone size is 1,320 square feet, and this equates to a standard width of 30 feet and floor profiles up to 44 feet. 44 feet is our maximum manufacturing length. We'll discuss it later, but it's not the longest length that we can utilize for floor profiles. But our standard zone sizes that reduce the amount of complexity and help make things consistent is to utilize this 1320 number and always provide a standard width of 30 feet. Trench layouts, the ideal layout is typically to utilize a monoslope, so a continuous slope from the back wall of the hangar down to the hangar door, and then provide trenches at equal spacing so that we have standardized profile lengths. So here we're showing an example where each of those profiles is 44 feet in length. However, if this was a shallower hangar bay, we would maybe be able to reduce these profile lengths. But again, the key here is that we have consistent trench spacing to minimize the variety of different profile lengths that we're working with. And then whenever we're looking at trench layouts, we reference back to that FM datasheet where we want to make sure that we're arranging trenches such that we don't have spills going under adjacent aircraft and exposing them if that fuel is ignited. There are some caveats to this or some exceptions. And so this is one specific example. This was a new construction hangar that we were helping to design. And the initial layout design was with that monoslope from the back wall to the hangar door. We did equal spacing on trenches at 39 feet. And this led to, a continuous slope with 4 trenches evenly spaced throughout the hangar. As we went about the design of this project, we realized that there was a substantial cost savings and reduction in construction time if we were to reduce this down to a 2-trench layout. And so by modifying our slopes so that we're sloping down to just these 2 trenches, putting a high spot in the center of the hangar, we're able to help cut cost as well as reduce construction time. So although the monoslope from back wall to hangar door is typically the first option that we want to consider, there may be hangars, depending on the depth, where it makes more sense to go to a different trench layout. So diving into some examples. First, we're showing a new hangar, currently working on install for this hangar. This is following NFPA 409 guidance for the layout, and it's a hangar housing a single aircraft, which is a P-8 Poseidon. So here you can see the hangar space with the aircraft in its dedicated parking position. From here, we identify fuel-containing parts of the aircraft, so fuel tanks and engines, and provide an 18-foot spill radius off of the outermost points of the aircraft. Based off of those spill radiuses, the design is just a simple rectangle, right? So we've got an 81-foot depth, 170-foot width. We've provided Safespill flooring in all of the areas where a spill could occur. And there was some consideration in modifying this design. And you'll see this in some of the layouts that we've shown, basically to cut off these corners because these are areas where there's no chance of a fuel spill based off of our spill radius methodology. However, as we went about this design, we determined that the additional manufacturing and construction complexity that would be required for this did not outweigh or was not worth it in terms of cost savings. So ultimately, the design ended up looking like this. We have monoslope from back wall to hangar door, reduced footprint in the hangar. Ideally, these trenches would be evenly spaced. However, due to the structural columns in the hangar, we had a footing right here where it wouldn't have made sense to have a trench with drainage out of the hangar intersecting with that column footing. And so in this case, we pushed that trench back slightly. We have profiles that are at 30-foot and 49-foot lengths. Just to give a little bit of background on what these trenches look like, whenever Safespill installs trenches in a hangar, we provide a hollow aluminum trench shell. This is pre-installed with plumbing and electrical, and these are delivered on site, anchored down to a base slab that's poured on in the excavated areas of the construction site. And then once these trenches are located, we actually backfill with concrete around this. So just to show some photos from the actual installation, here you can see the excavation area with that base slab poured. Once that's done, we place and align and anchor down these trench shells, connect all of our utilities, and actually use that trench shell as formwork to pour the slab around. In new builds, we typically utilize a recessed floor design. So the height of the ILDFA flooring is about 2 inches in height. So in new construction, it's quite simple to pour a 2-inch recess in all of the areas where the ILDFA is going to be installed. And this allows us to eliminate the need for ramps around the perimeter of the flooring, and provides a smooth, clean transition from the surrounding concrete floor onto the ILDFA surface. This is pulled directly from our design guideline, but it discusses an important consideration with construction tolerances. So when we do that recessed floor design, we always slightly oversize the recessed area relative to the ILDFA footprint, so that we ensure that the floor is going to fit inside of that opening. And then this gap is filled after the installation is complete. To fill around the perimeter of the floor, again, it's typically a 1 to 2 inch gap, and we fill it with a high strength epoxy to provide that seamless transition. Example number 2 is an example from a retrofit installation that we did for an existing hangar at Pratt & Whitney in Mirabel, Canada. In this hangar, they were phasing out their foam system, wanted to go with ILDFA. There were existing trenches in this hangar that run parallel to the fuselage, with existing slopes that go outward from the center of the aircraft, and go from the hangar wall into this trench. So this is a little bit different than, this was following FM data sheet 793. This is a little bit different than the trench guidance that they typically provide, but because these are 2 separate hangar bays, and these aircraft are, it's a dedicated hangar bay for this specific aircraft that's always parked in the same location when it's brought into the hangar, there's no chance that we're going to expose adjacent aircraft with this trench configuration. So knowing what we did about this hangar, it's a good candidate for a parking spot configuration. We have existing trenches that we can work with, existing slopes that meet the needs of the ILDFA system. And so our goal was to, do minimal changes to the existing infrastructure. So the first step in this was identifying fuel tank locations, ensuring that we have those spill radiuses accounted for. And you can see this orange line represents the footprint of the flooring system around the aircraft. We've got slopes going back into our trenches on either side. So we intend to reuse the existing slopes and trenches for the hangar. You can see this orange line it's actually a rectangle. Those are ramps because this is a retrofit application. So there is some additional standoff for those ramps. One of the challenges that we ran into on this application was that these trenches were too shallow for the amount of fire protection water that was going to be used for the hangar. This wasn't necessarily an ILDFA specific thing, but more of just changes in fire protection approaches over time to where they had been slightly undersized during initial construction. So we did have to actually excavate and retrofit, install new trenches in the area where the ILDFA was going to be located. In addition, a challenge with this is that it was a 110-foot span between the trenches on each hangar bay. So that means we need a 55-foot profile to cover this area, and that's slightly longer than our typical manufacturing capabilities. Finally, there was a platform that was located here, a permanent non-movable structure. And so we needed a custom design to go around that platform. We ended up, as I said, excavating and installing new trenches in the area where the ILDFA was going to be located. This allowed us to pass plumbing and electrical utilities through those trenches and accommodate the fire protection water that was expected. So we cut through the concrete slab, excavated and compacted in this area. Everything was done inside of an isolation tent with HEPA filters, so we didn't expose the surrounding operations to dust and debris. Once this was excavated and compacted, we pour that base slab and place those retrofit trench shells inside of the opening. Additional rebar was required for reinforcement of the hangar slab. based off these changes. And then once those trenches were located, we filled around the trenches with concrete. For the profile lengths, again, we needed to go beyond our maximum manufacturing length of 44 feet. We needed to cover a 55-foot span. So we developed an end-to-end field joining method where we were able to extend these profile lengths to 55 feet in the field on site. And you can see a photo here of that finished solution. Pretty seamless transition once the hatch covers are installed. In addition, to go around the columns for that platform, we opted to use a solid aluminum ramp-like structure. So this has slope back to either side so that anything that spills on top of this area is redirected into the floor profiles. So for existing columns and platforms, this photo is a little bit blurry, but you can see this aluminum cover that was constructed that pushes flow to either side back into the flooring system. The initial design for this was to just fill with concrete and slope it out, which we had done in previous projects where there were columns within the span. However, we opted to go with these removable aluminum covers rather than this concrete solution so that there was still access to the bolts at the bottom of these columns. And then for this project also, since it was a retrofit, ramps were installed around the perimeter of the flooring. Anywhere that we have aircraft entering or exiting the floor, we need to accommodate that 2-inch rise for the floor profile. So we provide a ramp with a 1 to 24 slope. That means that these ramps extend about 4 feet out beyond the floor footprint. In other areas where there's only light equipment or personnel moving onto and off of the floor, we're able to utilize a steeper ramp that has only a 1 to 12 slope, has about a 2-foot standoff from the footprint of the floor. And finally, a common thing that comes up with retrofits is that the slab may have shifted over time. We always want to make sure that we're meeting the required slope for these hangars with at least a 0.5% slope. And so in order to do that, we don't necessarily modify the concrete, but rather we utilize a shimming method just to elevate and slope the floor profiles during installation. So here's a couple of examples of shimming process that we used for that floor. Our last example is another retrofit application. This is for a NAVFAC hangar. This was an existing hangar with monoslope from the back wall to the front door. The only trench located in the hangar was at the hangar door. And so we did need to add additional trenching as the depth of this hangar is about 108 feet, too long of a span for a single set of profiles. Here you can see the aircraft with the spill radius bubbles around it. Because this was a NAVFAC application, we wanted to provide the maximum extents or a wall-to-wall solution for this hangar. Although the footprint could have been reduced based off of the aircraft, this gives flexibility for changes in aircraft over time and conditions where more than the usual number of aircraft need to be moved into the hangar. So this is the final design for that hangar. We added 2 intermediate trenches within the hangar, connected them in the center with this connecting trench. We were able to utilize equal profile lengths of 44 feet. So we standardize all these zone sections to reduce the manufacturing and installation complexity. And then we have a clearance to the back wall to allow for egress. In addition, along one wall of the hangar, the floor actually butts up to structural columns for the hangar. And so in that area, we provide a sloped concrete surface that gives a seamless transition, ensures that spills always go back into the floor. And then in addition, there's a pump skid that's located at the front of the hangar. This is to pump out anything that's spilled into those trenches. This is always provided with a reinforced bollard frame to protect the equipment inside from damage if a collision occurs. So just to kind of wrap things up, some common design challenges that we can always work around, but are really important to know about early in the design phase so that we can address them and come up with solutions. First of which is uncommon slope arrangements. So we've seen hangars where there's no slope in the hangar, and so we need to artificially create slope. We also see sometimes a configuration like this, where we have trenches that go around the aircraft. And we've got a high point in the center that slopes out at kind of a funky angle. And in retrofit hangars like this, we do have a design where we can accommodate these slopes and utilize them without making too many changes to the substrate. But again, this is a design challenge that we need to know about early on just so that we can work around it from a design perspective. The other common challenge that we see is a lack of existing drainage. So this may be a hangar like we just looked at, where there's only a trench at the door. We've seen hangars where there's just spot drains that are installed. And so that's not adequate for the drainage that's required for an ILDFA system. So in these hangars, we typically need to, even if there's a trench at the hangar door, we typically, depending on the depth of the hangar, will typically need to provide an additional trench at the midpoint and at the edge of the floor. Other common design challenges are obstacles like the platforms that we discussed with that Pratt & Whitney project, columns and permanently mounted equipment. Again, these are things that we can work around, and we have worked around them on previous projects. But it's just important to know about these early in the design phase so that we can come up with an optimal layout to address them. And then one of the other common design challenges is when an engineering design firm takes on a design, we often see that there may be oversizing or undersizing during that initial design. So oversizing would be designing wall to wall when a parking spot configuration could work for that hangar. Undersizing would be an example of only addressing the areas where fuel tanks are located, but not addressing spill radius. And so these variations in design can cause challenges as we work through the design and make it more difficult to execute the project. So best practices for success: always engage Safespill early in the design process to verify that layouts are going to work. So this verifies that we have the manufacturing capability and the constructability to make those layouts work. Also confirming that floor coverage aligns with code requirements. So making sure that we're using the proper standoff distances and that we have the proper trench arrangements in a hangar. And then other best practices are, the design guidelines are a really valuable resource. It has a lot of good information. And there's important construction tolerances that are noted in that document, particularly involving the additional gap or oversizing of that recess for new build projects and ramp standoffs that need to be accounted for on retrofit applications. So just to summarize, the simplest design for ILDFA is to go wall to wall, but under certain conditions, the ILDFA footprint can be reduced to a parking spot configuration. In those conditions, it depends on the day-to-day hangar operations, the type of aircraft, and the variability and flexibility that's needed in that hangar. When designing for ILDFA, always account for locations where aircraft fuel tanks and engines are located, but also address spill radius, which is either 16 feet for small aircraft or 18 feet for large aircraft. Always 18 feet for projects following UFC 421101. And then best practice for design. Our first initial design will typically always be looking at an application where we can go with a monoslope from the back wall to the hangar door. However, once we have that initial design, we want to try to minimize the quantity of trenches in the hangar. And so sometimes a monoslope might not make sense. When we're trying to reduce trench quantity, we may want to go to that kind of accordion style design. And then finally, best practice is always to standardize profile lengths and zone sizes so that we reduce manufacturing and installation complexity. With that, I'll wrap up today's presentation and open it up for Q&A. Okay. Okay, so a couple of questions we've got here. Is the whole facility sloped typically? How does Safespill work to resolve threshold conflicts with U-shaped facilities with supporting offices and workshops flanking the ILDFA area? So hopefully we answered this. That monoslope from back wall to hangar door is often an advantageous approach, but depending on the facility, we've gone into facilities where it's a retrofit and there may not be an existing slope to it, or maybe the building or structure has already been designed with no slope, and so we do need to put kind of intermediate slopes in there. So hopefully that answers your question, David. And I see you've got another one involving can Safespill work with a butterfly slab installation? Could you provide me a little bit more context on what you mean by butterfly slab installation? And then, have you seen any installations completed in facilities with radiant slab heating, glycol based? Are the two systems compatible? So yes, we have done to this point, we've done two projects that have in-floor radiant slab heating for these applications. If it's a retrofit, it's important to locate trenches, and we may need to modify the routing of that radiant slab heating to go underneath the trenches that are installed. If we don't need to modify trenches in any way, or if it's a new build facility, perfectly compatible with it, that radiant slab heating is routed in the same way that it would be, just going around the trenches. So again, with radiant slab heating, the only issue is that if we're excavating and we would be cutting through the tubing, we need to modify the routing for that to accommodate it. I see some in chat. Christian, sorry to arrive late. Is there a way to get a copy of the slides? So again, today's session is being recorded. And so everyone who attended the presentation today will have access to the recording of this webinar. Okay, and then there's a question about if there's a need for other fire protection measures in an MRO hangar for fire incidents like electrical faults. So, and if all of these codes that we discussed today, ILDFA is not the only fire protection system involved in the hangar. In addition to an ILDFA, you always need to install a water-based sprinkler system overhead. And so the intention is that is there to address other fire risks in the hangar. And ILDFA is specifically addressing the risk of a pool fire from a fuel spill. Okay, with the dual slope shown with example 2, is there any offset required between the profiles that are sloping to opposite trenches, or are they tight to each other? Let me navigate back to that example. I believe that's the Pratt and Whitney. Okay, so we're talking about this example. Is there any offset required between the profiles that are sloping to opposite trenches? So may need some clarification on this, but gonna do my best. So in this application, we do have a high point that runs along the center of this floor. We have floor profiles that run from the trench to that high point, and along that high point, we have a flushing manifold, and we have a cover that anchors down that end of the floor. And so there is it's probably a 4-inch wide space where we don't have the standard floor profile, but rather we have this anchoring element. And there will be some gap between those two pieces that butt up to each other. And so that's typically filled again with that epoxy filling, like we show. Where is it? Like we show here. Yeah, so at the high point, directly underneath the aircraft, we would have sort of an anchoring element that would need a fill between it. So hopefully that answers that question. Where you didn't have it, so but you eliminated true trenches. Yeah, so same idea with that other example. So in this example, right? So the floor profiles are not continuous in this space. There's floor profiles that run from this lighter blue line down to this trench. And this is actually indicating that there's a flushing manifold that's located here. So where that flushing manifold is located, there's an anchoring element that covers and anchors the floor down at that high point. And there will be two of those that are butted up to each other. I'll follow up with you and show some better pictures. I just don't have them in this slide. But John Mark, I'll follow up with you on that. Are you able to provide any guidance for space planning for ancillary equipment associated with the ILDFA pumps, flush system for a room? Any need for proximity to the floor slab? So this would involve, let's say, water tie-in or a booster pump. Typically, we'll locate that in a equipment room that's nearby. I can follow up, Carrie, and send you specific specs, but it's typically a 3 to 4 inch pump, maybe a 25 horsepower motor. So not a huge amount of space that's needed for that booster pump. I did show a photo of a pump skid. The pump skid is typically about 10 feet in length and about 5 feet in width. So we've got a footprint here of about a 5 foot by 10 foot area where that pump skid will be located. And it is important that that pump skid is located relatively close to the pickup points or the end of those trenches, so that we can maximize the flow rates that those pumps are able to handle without oversizing them. But we can also place this pump skid on the other side of the wall and weatherize it to be in outdoor conditions. So hopefully that helps, Carrie, and I can follow up with you more on those questions. Amy asked, you mentioned that NFPA 409 and FM global standards. So asking about process by which you went through these compliance checks and provide documentation to support this. Yeah, so ILDFA, first step was ILDFA Safespill floor being FM approved. So we went through the standard FM approval process to get the product FM approved. From there, we did a series of fire tests and began discussion with the NFPA 409 technical committee, submitted a lot of testing data, attended technical committee meetings to help substantiate the performance of ILDFA. And from there, it was just working with those code development bodies to determine what requirements were needed around this type of system. So hopefully that answers your question, Amy. The other question, there are some gray zone interpretations on, for example, the requirement to have a storage tank for holding spilled fuels in NFPA. Do you have guidance document on the sizing of this tank? Yeah, so again, not really related to layout and sizing, but we do have a white paper on our website that specifically talks about options for containment and drainage, storage tanks versus oil water separators, those types of things. Aaron asks about aircraft washing water drainage. Yeah, the ILDFA can be used for aircraft washdown. Is Safespill able to adjust the water distribution design to accommodate an incoming water pressure that falls outside the pressure specified in the design guideline? Again, not really related to. Yeah, so we're, again, for flushing water, we are able to install a booster pump if we need to boost that pressure, or a pressure reducing valve if we need to dial it back. Okay, so David followed up to rephrase, is the accordion style or butterfly? Okay, so you mean that constant slope. So I do believe that UFC guidance is that a monoslope is preferred, but for all slope designs, the slab thickness is not reduced because we're including the ILDFA in there. ILDFA works in compression. It's not adding structural support to the actual slab. So that slab needs to be designed in the same way as if there was no ILDFA on top of it. So David, hopefully that helps. But for instance, if you were doing a design for a hangar slab that didn't utilize ILDFA and you needed a 10-inch slab to provide proper structural support, if you add that ILDFA in there, you still need a 10-inch slab underneath it. So you're not reducing it down to an 8-inch slab to account for the 2 inches of flooring. You're keeping that constant slab thickness. So hopefully that helps. Okay, so we got a question again about containment tanks. Again, I'm sorry, guys, not the focus of today's presentation. We do have resources on the website with a white paper talking about containment and drainage, and that's something, go check out those resources on our website. And if you still have questions, please follow up with me in an email and we can discuss that. Okay. Can the fire pump for ILDFA also serve the overhead sprinklers? Yes, it can, as long as it's sized for the flow rates for both the ILDFA and the sprinkler system. Can you share the FM approval documents with me and testing results from the fire testing you did? So, Amy, all of these documents are FM approval standards, and all of our 409 testing are on our website, publicly available. And then there's a question about electrical grounding. Yeah, so this is integrated into the flooring system. We install grounding points retroactively in the floor surface. And there is a section in the design guideline that specifically addresses grounding points. So Abigail, recommend go find our design guideline. I can send it to you if you don't have access to it. But there is some discussion there that shows electrical grounding. Okay. It looks like we're not getting any new questions. There are a couple of these questions, like I see Nicholas, Abigail, Maxime, around questions that are outside of the scope of layout and sizing. I'm going to follow up with you guys directly after this and answer those questions via email. But do we have any additional questions related to layout and sizing in today's presentation? We'll give a couple minutes for people to drop additional questions if they'd like, and then we'll go from there. Hey everyone, thank you for attending today's webinar. Hopefully this was helpful in your design considerations for any projects going forward that you have with ILDFA. Again, really appreciate everyone attending. This was recorded, so everyone will have access to this after the fact if you want to go back and look at it. I'm not going to send out slide deck, but you can go through and see all of the slides that were shared today. And in the future, we will do more of these presentations, and we should be able to share these on our website moving forward, so they're publicly available. And any questions that were kind of outside the scope of layout and sizing, I will follow up with you guys directly via email. Thank you.